Engineering Dynamics, Session 9, Kinetics of a Particle, Curvilinear Motion in a Normal and Tangential Format. So in this problem, we review a curvilinear motion. So we have a ball which is moving in a curvilinear path, like what you can see, like capital S, started from the origin at O. If we just draw the velocity vector, that velocity vector is equal to velocity times normal in t, normal vector tangential form. Also, there is a normal unit vector to the origin of the curve. So we can call velocity vector is equal to amount of velocity times normal at t. Acceleration is a derivation of velocity, and that's v naught, and it's just make a derivation of this term, that's v naught times ut plus a derivation of second terms u prime t times the first term. If you have a closer look to what's happened to a ball which moves on a particle, a ball which moves in a curve like ds, the unit vector in tangential format at the first location is ut, and it just replaced in ds curve, it just moves to a bit farther, that's u prime t. So a, let's focus on acceleration, it's v naught, and that's v naught times ut, normal vector in tangential form, that's a tangential unit vector, that's normal unit vector. So v naught is clear, but let's see what is a time derivation of ut. Ut naught, time derivation of ut, which we call that u naught, is like when you keep a closer look to the ball, you can easily see as the particle moves along the arc ds, in the amount of dt in time, the magnitude remains unity because it's ut. However, its direction changed from ut to u prime t. Both of them are unity vector, but it just moves from ut to u prime t because we are just moving on the curve. So then what's happened in infinitesimal, a small arc of radius ut is equal to 1, and that means our time derivation of ut, if you look at the t, that's 1 unity times d theta. What does that mean? It just means there is an angle between t and u prime t, as we can see here. The difference between those is dut, and the difference of them is unity, and then it's time d theta. So that's infinitesimal small, and that's, we can consider that as a unity because that's a displacement between two unit vector, two different time span, and that's a 1 or unity times d theta, which is the angle. And definitely there is a normal. If you look at the direction of the normal, it just point out toward the y-axis, that's a un. So we can call it, simply we can say its direction is defined by un, because it just points toward the y-axis, and that's un. So we can call or rearrange the dut like d or 1 d theta because we just didn't rewrite the unity. 1 times d theta from the top over here. Then times un, which is the unit vector of what we are talking about. So one can say u dot t, you can replace du of t by u dot t, that's d theta, replace it by theta dot times un. As soon as we have that, at the same time we do know ds, the displacement in the curve, is equal to rho times d theta. It's the radius times of curvature times d theta arc you're moving along that. And you can also show that by s dot is equal to rho times d theta. They are identical to each other. So if you just rearrange the second equation base of theta dot, that's s dot over rho, that's s dot over rho, we call equation 2. The first one, u dot t is equal to theta dot times u, and 1 and 2 each other, it just says u dot t is equal to, if you just replace theta in this equation, it just says s dot over rho, then un. At the same time, we do know s dot is velocity. The derivation of displacement is over time is velocity. So you can easily replace u dot t by v over rho times un. If you just we just have this one, and if you just plug it into equation for acceleration, it just says a acceleration is the derivation of velocity over time, and that's v naught times ut plus v times dot t. So we just create this one, we can replace it in the main formula to see how it goes. As soon as we replace it, it just says a is at, tangential component of acceleration, a plus an times un. And if you keep a closer look to the equation, it just says these two are identical. V naught is equal to at, because this is v naught times ut, this is at times ut. It just says v naught should be exact value of at. And in the other part, it just says v times u naught t is equal, it should be equal to a n u. And if you just replace u dot t, like u is equal to v over rho times un, v over rho times un, and it just says we have another v here, so an, this un by this un is cancelled out, we have v squared over rho, that's our an. So 1 and 2 simply says an is v squared over rho. So we can easily say the two component of acceleration, the tangential part and component is the tangential component and normal component of acceleration are v naught and v squared over at is equal to v naught, and an normal component of acceleration is v squared over rho. And the magnitude of acceleration field is square root of at squared plus an squared. So again, at is v naught, an is v squared over rho, and a, the magnitude of acceleration, that's the magnitude of acceleration in n and t format, normal and tangential format, that gives us this equation. Let's put it into an example. So in this example, we have a car like C travels around the circular track that has a radius of 300 feet, like figure below. If the car increases its speed at a constant rate, an increase in speed in a constant rate, it means there is acceleration. All the time, the given number is 80. Don't forget it. We are provided with, if you find a numeric value and there is no name of that, that's definitely a tangential component of acceleration. So we know tangential component of our acceleration is 7 feet over second squared. And starting from rest, it just says v naught is equal to 0. Rest means there is no initial velocity. We want to determine the time needed to reach an acceleration of 8, and that's definitely total acceleration, which is at squared plus an squared. So before starting the problem, we already know we are looking for an, and also what is its speed at this instant. How long does it take to reach to acceleration? So what is the t? And then as soon as you know what is the t to reach the a total of 8 feet per square second, we need to know what is the speed on that. So if you just replace that in the equation of speed or velocity, you can easily get that. Let's approach our problem. So to start solving this problem, A is the square root of a tangential component of acceleration plus normal component of acceleration, and at is divided in problem statement like 7 feet per square seconds. We already know from normal and tangential component an normal component of acceleration is v squared over rho, and v is v naught plus at in a horizontal. So that's a v is equal to 0 plus 70, because again that's a t times t in a normal in horizontal movement, and it just gives us an is 70, because velocity is equal to at, velocity is 70. If you replace it in here, it just says that's 7 times time in parentheses squared over rho, which is provided to be 200. It just gives us an like a parametric equation of 0.6, almost 16 t squared feet over per second squared. And as soon as we have that, by replacing that in the equation of total acceleration, if we just replace this numeric value in acceleration equation, it just gives us a total time. What is the time needed to reach to acceleration of 8 feet? We just replace acceleration like the total formula for acceleration, like 8 feet per square seconds, and this is the at component, an component, like just directly comes from the down here, and it just says it just takes almost 5 seconds to reach a total acceleration of 8 feet per square seconds. And if you replace that in the equation for a speed, it is 7 times t. We already calculated this equation. And if you replace the numeric value of time in the equation, it just gives you a velocity of 34.1, and that's feet per second, because we are working on CS customer unit. Thank you. We'll work more problems in next videos.